Greetings and welcome to another edition of Joe's Laboratory. In this exciting episode, I'm going to check the torque of all the fasteners in the bottom end of this Chevy small block, since I've already installed the entire reciprocating assembly. I've only now progressed this far because I found 3 additional problems with this block since I made the last video of my wrist pin oiler test. The first problem I came across while I was testing the wrist pin oilers. I noticed then that the nozzle for cylinder 3 didn't squirt quite as well as the others. Apparently I'd opened the orifice of the nozzle up a bit while pulling the wire out that I'd stuck through it to show the typical oil stream trajectory in my last video. When I decided to replace the number 3 nozzle, my aircraft AP asked me to get an extra nozzle to replace the one for cylinder 8 as well. He had bent the nozzle for cylinder 8 a little too far in an attempt to stop the oil that came out of it from roping up on the oil pump drive shaft. Although he did successfully accomplish that and managed to bend the nozzle back where it needed to go, he was afraid he had fatigued the brass too much and that it just might break off at some time in the future. Second problem was that my rear main bearing cap was leaking oil where the tip of the outer lip for the oil pan seal was missing on one side. I tried to use this cap, which came off my old block, but since it wasn't a line board with this block, it wasn't cut deep enough, so I couldn't do it. Fortunately, my AP friend was able to save my broken cap by putting a pin in where one of the tips was missing and then shaping a new tip over it with metal epoxy and a file. Then, as he cured the epoxy in the oven, he found that the tip on the other side was cracked as well, and he ended up drilling and inserting a pin in both sides. He did a great job on saving my rear main cap, as well as taking care of the third problem, which was the hole in the main oil gallery plug in the front. I had asked the machine shop that did the lion's share of the work on this block to drill a 30 thousandths hole in the front main oil gallery plug. But when I conducted the wrist pin oiler test, it was obvious that the hole had been way over drilled. We were able to stick a 40 thousandths drill bit right through it. To fix that problem, my AP friend drilled and tapped the plug for a 632 thread, then fabricated a brass nozzle with a 30 thousandths orifice in it and threaded it into the plug. He then removed the rear main gallery plug and ran a magnet through the main oil gallery just to make sure he didn't leave any chips behind. Now all of that is good. After that was done, the wrist pin oiler nozzles for cylinder 3 and 8 had to be drilled out so we could replace them. We hated to resort to drilling them out, but since we had put all the nozzles in with Loctite, we really didn't have any choice. It wasn't really that big of a deal though, because we still had both of the original drill guide blocks that we had used to make the nozzle holes in the first place. With these last 3 problems with the block out of the way, I did one final wrist pin oiler test and then made sure that all the nozzles squirted just the way they were supposed to. Next, I mocked the block up with pistons and checked all the rod bearing clearances. I bought 21 thousandths oversized bearings because I'm running a steel crank that's not only been cut 20 thousandths under, it's had 12,000 miles of wear put on it, in addition to having the diameter of the bearing journals reduced even farther in the process of having the crank polished. However, After seeing how close the rod bearing tolerances were with the 20 thousandths oversized bearings I put in, I ended up only using 3 of the 16 halves in this box of 21 thousandths oversized bearings. I used 2 of those 21 thousandths oversized bearings in rod number 1, and I used 1 of them in rod number 2, just so that the clearances for this pair of rods was the same as the rest of them in the crank with 20 thousandths over bearings. According to the plastic gauge I used to check, all rod bearing clearances are now somewhere between 1 and 2 thousandths of an inch. That's on the tight side, I know, but with a forced induction engine that's for the street, that's where I'd rather be. With 9 30 thousandths oil jets squirting all the time, I don't think the tight tolerance of the bearings is likely to overtax the drive of the high volume oil pump. According to my 1978 edition of Chevy Power, the main bearing studs are supposed to be torqued up to 70 foot-pounds with moly coat on the threads, and the rod bearing bolts torqued up to 50 foot-pounds with nothing but oil. Moly coat is a trademark name for Dow Corning's molybdenum disulfide grease, just like Ultra Torque is the trade name for ARP's moly grease. I didn't have either one of those greases, but fortunately my AP friend was able to spare a little mil-spec high-pressure moly grease that he was given at the hangar where he works. Now, all my 7/16 main studs are torqued to 70 foot-pounds with moly grease, and all my 3/8 rod bolts are torqued to 50 foot-pounds with oil. I often use a kind of clip wrench torque wrench, like Harbor Freight Special here. But when it comes to doing my final torque pulls, I prefer to use a torque wrench that has a gauge needle on it, so that I can actually see how much torque I'm pulling as I'm pulling it. To do a quick check for this video though, I'll just use this click wrench, because even zoomed in, the needle gauge of my other torque wrench would be really hard to see. Right now it's adjusted for 70 foot-pounds, so I'm going to check all of the mains, starting with the one in the very front. Now the outer ones. These are actually in Chevy Power as 65 foot-pounds, but I already torqued them up to 70, so 70 they are. I don't think 5 pounds is going to make that dramatic of a difference on bolt stretch. Now that they're all at 70, turn the torque wrench down another 10 pounds, or 20 pounds rather, and go to 50 for checking all the rod bolts. I'll have to turn the crank once, but it's not a big deal. Just checking for number 1. Two. And 3. 4. And now I gotta rotate the crank 180 degrees to get the rest of them. It's still pretty stiff because it's got new rings in it. Here we go. Should be able to get the last ones now. Here's 5. 6. 7. 8. It's the rod bolts that I'm always paranoid about. Too much stretch, you can break them. Not enough, and the nuts could back off, which is even worse. All these rod bolts are torqued to at least 50 foot-pounds, so now I can continue on with the rest of the build. Installing the windage tray and the oil pump is pretty much of a no-brainer since I'm using the same high volume oil pump, pickup tube, and oil pan that I used before, so I'll get to that later. Next to go on is the timing cover and the cam sprocket so that I can use a dial indicator to check the camshaft in play. This 2-piece aluminum timing cover has a removable plug so that you can put a dial indicator, set it up, go through the hole, make contact with your cam sprocket so that you can set the in play of your camshaft. The cam sprocket has got a big Torrington bearing on the back of it, and it's got a steel button with a small shaft that fits into the front. It also has a little tiny Torrington bearing on it with a rotor that goes on top that makes contact with the back of the timing cover. By putting thrust washers in between the small Torrington bearing and the rotor, you could set the camshaft in play. Well, I guess I've about covered everything I need to cover on this one. So, until the next video, happy hot rodding, everybody.